This section of the training is going to be looking at how to get started with your OpenSPR experiments. Here is a list of recommended steps to consider when setting up and performing a binding experiment. We will be going through and reviewing each of these steps in detail, but first we'll look at sample considerations for your binding system. One of the first things to do when planning an OpenSPR experiment is a literature background search on your binding partners. This would include looking for any past binding kinetics data, which could provide useful information on the potential binding affinity and sample conditions for your experiment. Factors such as molecular weights, tags on the molecules, isoelectric points, and additives provided in stock solutions can help determine which binding partner should be used as the ligand and which will be used as the analyte. Next, you'll have to determine the conditions that are necessary for the required binding interaction to occur. And lastly, you want to ensure that your samples have been purified and are homogeneous. The next thing to consider is the sensor chemistry for the application that you're going to be analyzing. So the one requirement to perform SPR interaction analysis will be to immobilize one of your binding partners onto the sensor surface. Here I have a picture of one of our sensors, and this consists of a glass slide, with the red spot in the center being our nano gold particles. Now, as mentioned earlier, these nano gold particles are going to be performing all of the detection for us. Now, in order to immobilize your biomolecule, we offer a wide range of surface chemistries to make this as easy and seamless as possible. So when you're starting out with a new binding system, you'll need to decide which sensor chemistry will work best for your samples. Now, if your biomolecule contains a tag, for example, a histidine tag, a GST tag, or a biotin tag, you can take advantage of this and immobilize them onto the surface via these tags using one of our capture coupling techniques. Now, if you're working with a biomolecule such as a protein without a tag, you can take advantage of a direct coupling technique. The most common one we have is our carboxyl sensor surface, which uses an EDC NHS amine coupling technique that will covalently couple any free amine groups to the sensor surface. Now, if you're working with a biomolecule that needs to be in a hydrophobic environment or liposomes, you can take advantage of one of our hydrophobic coupling techniques. Now, for each of the different sensor chemistries, we have a respective sensor chip tech guide which will walk you through the procedure for using each chemistry. Now, once the ligand has been covalently immobilized, it can no longer be removed from the sensor surface. Thus, covalent capture sensors can only immobilize a ligand once. Now, ligands that have been immobilized via capture coupling sensors can sometimes have their ligands removed and the sensor reused to immobilize a new ligand. However, this cannot be done with the biotin-streptavidin interaction, because this is essentially an irreversible interaction. Now, a sensor may be reused. However, this is dependent on the sensor handling, storage, and ligand stability. And it is recommended to test a reused sensor with a previously tested binding interaction to ensure that the sensor is fully active and has the same binding capabilities. Now, it is recommended that a new sensor should be used for publication quality results. Now, once you have your sensor chemistry chosen, the next thing you'll have to do is focus on your buffer and sample preparation, because the quality of sample preparation will be key for obtaining accurate binding kinetics. So first, you'll want to ensure that your running buffer is properly pH. You want it to be filtered, most commonly using a 0.2 micron filter, and this is just to remove any aggregates or dust which will prevent them from accumulating within the tubing of the instrument. And you want your running buffer degassed, which will prevent any accumulation of microbubbles within the instrument. And if you're using some unstable additives, you'll want to prepare a new buffer every day. Now, the most important thing to remember is that you need your Analyte sample buffer to match the running buffer as closely as possible to avoid any background refractive index differences. So this means that you want to either directly dissolve or dilute your sample with your running buffer. because if the analyte sample buffer and running buffer do not match, you will see this mismatch appear in your data as a false positive shift. And I'll show you an example of that a little later on in the training. Now, the next thing we need to do is we'll need to check our analyte for non-specific binding. So once you've chosen your sensor chemistry and prepared your buffers, the very first test you should be starting with is a control test. And this control test is going to check your analyte for non-specific binding. So non-specific binding is when your analyte binds to something other than the ligand, often the sensor surface itself. And this is going to result in a false positive signal, which we don't want to have during the specific binding test. Now, there are a few ways to test for this non-specific binding. The most common option is to start by introducing the analyte over the initial sensor surface without the ligand present to see if we can measure any false positive signals. Now, the surface may be untreated, activated and blocked, or prepared with an inactive protein to mimic the physical properties of the active surface. So examples would be if you're performing non-specific binding on a carboxyl surface, you're going to want to activate it with EDC-NHS and then block it with your blocking solution. Whereas for your NTA surface, you're going to want to block that surface by immobilizing a histidine tag protein that would be considered inactive or won't bind to your analyte so that you can mimic the physical properties of your active protein. And then if you're using a streptavidin surface, this can be left untreated as the streptavidin itself will act as a blocker on the surface. Now, when running these tests, ideally you want to see no response from your analyte interacting with the sensor surface. However, if you do see a false positive binding signal, this is actually okay and actually very common, especially when working with a simple buffer solution such as PBS or HBS. And this is going to be the first point of experimental optimization. So what we have here now is just an example of how to block a carboxyl sensor surface. As I mentioned, you're going to start with activating the surface with EDC-NHS, and then you're going to skip the ligand immobilization step, and then inject just your blocking solution to block the sensor surface. Now for a one-channel system, this is done on a separate sensor. Whereas for a two-channel system, this is done in the reference channel. To reduce these non-specific binding signals, if you were to see any, again, this will be done by optimizing your buffer conditions, namely by including a variety of different buffer additives. And this is a standard technique across all SPR experiments, and it's not only unique to our instrument. So what I have listed here are the most commonly used buffer additives. For example, tween-20, which is also referred to as P20, can be included to help reduce hydrophobic-mediated nonspecific binding. BSA is a protein additive that is commonly used. Or if you suspect the interaction is more electrostatic mediated, you can add additional salt or adjust the pH of your running buffer. Now, the literature is a great resource for looking at starting buffer conditions. But note that the surface coating on sensors from different companies will vary, so we highly recommend testing specifically on our sensors. And ideally, you only want to proceed to your specific binding test once you reduce the non-specific binding as much as possible. So to continue that example of blocking on the carboxyl sensor to test for non-specific binding, what you will then do is inject your analyte starting with your normal buffer condition, which in this case would be our plus 0.005% tween. And then you're going to add different buffer additives to see if we can reduce the signal of our analyte on the block sensor. And as you can see from this example on the right, the curve in green, which has 0.05% tween and 0.1% BSA added, has reduced the nonspecific binding to 0. So these are the conditions that you will now add to your running buffer and your analyte samples for your specific test. Now that we have our nonspecific binding test done and the buffers that we want to use with our sensor chemistry chosen, we'll then go on to our ligand immobilization step. Now, So this means that we're now ready to start our specific binding test, and the first step will be immobilizing our ligand to the sensor surface. So as mentioned earlier, for each sensor chemistry, you're going to want to reference the specific sensor chip tech guide for a step-by-step protocol. And also, while immobilizing your ligand, we have a very useful equation here that you can reference, which I have expanded in more detail here. Now, this equation is used to estimate the maximum theoretical analyte binding signal that you will obtain in an SPR test, and it's depicted here as the Rmax. Now, the units of our response signal are nanometers or picometers. As remember, we are tracking a wavelength position. And then we can relate the analyte binding signal intensity to the molecular weight ratio between the analyte and the ligand, as well as the ligand immobilization level. Now, this term, the ligand immobilization level, is determined experimentally by calculating the net shift in the response signal during our ligand immobilization step. And this is very well outlined in our sensor chip tech guide. Now, say for example, if the molecular weight of our analyte and ligand are about the same, this ratio will then be 1. And if we have 800 picometer of ligand immobilization, we should then expect our analyte binding signal to be at a maximum of 800 picometers. Now you can tell that this equation will become especially important if the molecular weight ratio is small. So say we have a large ligand on the surface and our analyte is a smaller molecule. Now, when this ratio is small, we are going to want to ensure that we have sufficient ligand immobilization to be able to detect the analyte binding signal. Now, for our response units, you're going to want to aim to have at least an Rmax of around 50 picometers to ensure that we have a good signal-to-noise ratio for detection. Now, knowing all this, we can have a minimum goal for our ligand immobilization level. So what we have here is an example of a ligand being immobilized to the carboxyl sensor in our 2-channel OpenSPR instrument. Now, as you can see from this response graph on the right, both channel 1, which is in red, and channel 2, which is in blue, are activated by the EDC NHS. Next, the ligand is then injected only into channel 2, which is followed by an increase in the response for the blue curve and a flat line for the response for channel 1, which is the red curve. And then after that, we're going to inject the blocking solution into both channels. Now this will result in channel 1 being our reference channel and channel 2 being our active channel. Now, as was done for the nonspecific binding test, our reference channel may be either untreated, activated and then blocked, or prepared with an inactive protein to mimic the physical properties of our active surface. Now, one thing to note is if the ligand immobilization response doesn't reach that estimated level that you calculated for your Rmax, you should then perform a second or possibly even third ligand injection to get that response level high enough. It should be noted that you should not proceed to the analyte injections if the ligand immobilization level isn't sufficient to reach an Rmax of at least 50 picometers. Alright, so now once you have your ligand immobilized onto the sensor surface, you will now be able to work with your analyte injections. So as mentioned earlier, you're going to begin introducing your analyte to obtain your first binding curves. Now, if you remember during that part at the beginning of the session, you're going to need to obtain these binding curves at multiple analyte concentrations. Now, if an estimate of the KD is known, you're going to want to use a range of analyte concentrations between 0.1 times and 10 times the KD value. If no information is known for the KD, it's recommended to start at a low nanomolar analyte concentration and increase this until a response is detected in the instrument. You'll also want to be using between 3 to 5 analyte concentrations for your analyte injections. And you're going to want to dilute your samples using either a 2- or 3-fold serial dilution so that you can obtain ideal spacing between your different binding curves. Now, one of the most important things to remember is that you want to ensure that the analyte sample buffer and the running buffer match as identically as possible. Ideally, they should be identical with the exception that one has your analyte sample in it and one doesn't. And to do this, you should be using your running buffer to either directly solubilize or directly dilute your analyte samples. And as mentioned earlier, between each analyte injection, a regeneration solution may be necessary to ensure that we have the same number of ligand binding sites for each analyte concentration. And we're going to talk about this in more detail right now. So again, as I just said, before you start to collect your next analyte binding curve, you may need to use a regeneration solution to remove your analyte from your ligand because you want to ensure the same number of ligand binding sites are available for each analyte concentration that you are sampling. Now this regeneration solution, what it's going to be doing is it's going to be disrupting the binding of your analyte to the ligand, causing the analyte to be fully removed from the sensor surface. Now, if for instance your interaction has a very fast off rate and all of your analyte will dissociate on its own within 2 to 10 minutes, then all you'll need to do after your analyte injection is wait for the analyte to come off, and then you can proceed to the next analyte injection without the use of a regeneration solution. Now, however, if this dissociation rate is slow, it's not very practical to wait until it all naturally dissociates. In this situation, you're going to be using that regeneration solution to disrupt your ligand and analyte binding. Now, this regeneration condition is going to be completely dependent on the binding mechanism of your system. Now, to determine these optimum conditions, you're going to be introducing your analyte at a fairly high concentration that'll slightly saturate your ligand, and then you're going to screen for the optimum solution for your particular binding partners using a regeneration scouting procedure. Now, this can be done by trying out a variety of different solutions, which include either acidic, or basic, or ionic, or detergent. Now, as a general rule of thumb, you're going to want to start with the least, or you're going to want to find the least harsh condition that can get the job done. Because ultimately, this regeneration step is going to be shocking your ligand, and you don't want to damage it or alter its binding capacity thereafter. This regeneration condition is also recommended to be run at a faster flow rate to minimize the exposure time and any potential damage that may happen to the ligand. Now, as mentioned earlier for the non-specific binding conditions, the literature is a great resource for selecting your regeneration step. Because if a similar system to yours has been studied with SPR, because this is completely dependent on your binding partners and not the SPR instrument, those conditions should also work to regenerate this binding system. If a regeneration step is needed, once the optimum regeneration solution is found, it is recommended to precondition your ligand with this solution prior to your first analyte injection. This will ensure the highest consistency throughout your test. So for example, in this response graph below, our first step here is the immobilization of our histidine tag protein to our NTA sensor. And as you can see, there's a slight off rate that's occurring after this step is done. Next, we're going to precondition this ligand on the sensor with our regeneration condition. And you can see that some of the loosely bound ligand has been removed from the sensor surface. And this is stuff that probably wasn't captured via a histidine tag and was loosely interacting with the sensor surface. And after this, all of our subsequent analyte and regeneration steps all return to the same baseline, suggesting that we have a highly consistent test. Now, one thing to note with this is that our regeneration solution is going to cause a bulk shift, as this solution will differ from your running buffer, which will cause that buffer mismatch. And this is completely normal. We have now discussed the 4 main areas in the experiment that may require some optimization for your binding system. The first area we looked at was the non-specific binding, and this will involve optimizing your running buffer with different additives. The second area would be the ligand immobilization step, and this will be specific to the sensor chemistry that you are using for your binding system. and you may need to optimize this step to obtain a desired immobilization level. The third area that might need some optimization is your analyte concentration range. And as stated earlier, this is going to vary for each binding system. In general, you'll need to use a concentration range that's around your expected KD value for your interaction. And the final part of the experiment that may need optimization is your regeneration solution. And again, this is going to be completely dependent on the samples that you are analyzing.